Welcome to this next video in the playlist on ring theory. In this video what we're going to discuss is Eisenstein's criterion, which is a criterion for a polynomial in a ring of polynomials over an integral domain to be irreducible. Okay, so I'll start off with a statement of Eisenstein's criterion. Then what we'll do is we'll do an example, and then what we'll do is the proof of Eisenstein's criterion. Okay, so let's start with the statement. Okay, so we're going to be working with a ring of polynomials over an integral domain. Okay, so our coefficient ring is going to be an integral domain. So R here that we're starting off with is going to be an integral domain. Okay, so remember, an integral domain is a non-zero commutative ring where, in addition to just being a non-zero commutative ring, it's also true that whenever you multiply two non-zero elements together, you will get as your answer another non-zero element of that ring back again. Okay, so the only way in an integral domain to multiply two elements together and get 0 as your answer is if one or both of the elements that you multiply together is already 0. Okay, so we've got an integral domain here. Okay, and what we're going to do is we're going to construct the ring of polynomials over that integral domain. So we're going to construct R adjoin X here. Okay, so the ring of polynomials over the integral domain. And now Eisenstein's criterion is going to give us a criterion for certain polynomials, not all polynomials. It can only be applied to certain polynomials in this ring of polynomials over the integral domain to be irreducible. Okay, so let's say we have P of X here, which is an element of the ring of polynomials over the integral domain. Okay, now P of X, in order for us to apply Eisenstein's criterion to it, is going to have to be rather special, and the first thing I need to describe to you is what special properties does it need to have. Well, the first thing is that it needs to be non-constant, so that's easy to understand. We don't want it to be a constant polynomial. We want it to have at least one of the coefficients in front of a power of x to be non-zero. Okay, we don't want the only non-zero coefficient to be the constant coefficient. Okay, so we want it to be non-constant, and then we also want it to be monic. Okay, so those are the two properties that we're going to insist on. Now remember, monic means that the coefficient in front of the highest power of x has to be 1. Okay, the multiplicative identity of our coefficient ring here, capital R. Okay, so to write this out explicitly then, let's say I've got my polynomial P of X here. It will look something like this. P0 plus P1 times x plus all the way up to, and let's say it's degree n, so we'll then have x to the n here, and the coefficient in front of x to the n, as you can see there, is 1. Okay, so here is a non-constant monic polynomial, the sort of polynomial which we can actually successfully apply Eisenstein's criterion to it. Okay, so Eisenstein's criterion then, take a polynomial of this form then, and you can conclude, this is Eisenstein's criterion, you can conclude that this polynomial is irreducible. Okay, so it's irreducible in the ring of polynomials over the integral domain. Now let me just firstly remind you of what that means. So remember, irreducible is definable in an arbitrary non-zero commutative ring. Okay, and it's a term that can be applied to all non-zero, non-unit elements. Now, of course, this is going to be a non-unit and certainly a non-zero element within the ring of polynomials over the integral domain, because whenever you take a ring of polynomials over an integral domain, it's true that the only units in that ring of polynomials are going to be the constant polynomials. Any non-constant polynomial is not a unit, and therefore it is applicable to apply the term irreducible or reducible to one of these polynomials. So that's the first argument, that it's even relevant to talk about whether this polynomial is irreducible. Okay, that's one of the reasons we want the polynomial to be non-constant. Okay, so irreducible then, in an arbitrary non-zero commutative ring, it talks about elements that are not zero and not units, and an element that is non-zero and non-unit is called an irreducible element if all products that you can come up with in that non-zero commutative ring which make your element are trivial products, which involve a unit element multiplying with an associate of the element you're trying to make. Okay, so let me just write this out. So let's say R is our arbitrary element within our more general non-zero commutative ring. Okay, then if it's true that it is a firstly non-zero and non-unit element, and it's also true that all products you can come up with, all A times B products, where A and B are just elements of the non-zero commutative ring, so you go through and find every single product that you can possibly use that will make you this element R. If it's true that all of these products are rather trivial, i.e. one of these elements is a unit, okay, and the other element is then an associate of the element R, if those are the only products that exist that make this element, then the element is called irreducible. If that isn't the case, then there must exist some less trivial product, a product involving two non-unit elements being multiplied together to make this element R, and then the element will be called reducible, provided of course that it's not the zero element and not a unit element. Okay, so the terms reducible and irreducible don't apply to those terms which are zero or units. Okay, right, so this polynomial, p of x then, is going to be irreducible in the ring of polynomials over the integral domain, i.e. the only products then that are going to exist which can make it in the ring of polynomials over the integral domain are going to be a unit, okay, which of course will be some constant polynomial. Now we don't know that all constant polynomials are units, but we do know that all the units are constant polynomials, so it will be some constant polynomial times another polynomial which will have to have the same degree as this one, so it will have to have degree n. Okay, so what does Eisenstein's criterion then actually say? So Eisenstein's criterion says that we can conclude that this polynomial p of x here is irreducible in the ring of polynomials over the integral domain if it is possible, okay? If it's possible, so I'll put if there exists a prime ideal, okay, which is a prime ideal of the coefficient ring, the integral domain here, okay, so if you can find some prime ideal of the integral domain capital R, so this symbol here is just the symbol for is an ideal of, so P is going to be a prime ideal of the integral domain capital R, such that, okay, such that all the coefficients, P0, P1, all the way up to Pn minus 1 are elements of that prime ideal. However, P0, so but, P0 is not an element of P squared. Okay, now a lot of things in here need explaining. So firstly, let me just remind you of what a prime ideal actually is, and then let me tell you what P squared actually is. Okay? Right, so let me firstly remind you then what a prime ideal is. So a prime ideal is first and foremostly just an ideal of the ring capital R, but then in addition to just being an ideal, and it does have to be a proper ideal, it's not allowed to be the unit ideal, in addition to just being a proper ideal, it also has to obey the property that if you multiply two elements together that are not in that ideal, then you end up with something that is not in that ideal. So if I draw a little picture to remind you of what a prime ideal is, so let's say here is my picture of the ring capital R, and let's say this is my prime ideal capital P, and I'll just colour this in. So this box is representing all the elements in the actual entire ring capital R, which is our integral domain, our coefficient ring for the polynomial ring, and here then is our prime ideal, which first and foremost is a proper ideal, so it's properly contained within the ring capital R. And now to be a prime ideal, it must be the case that if you multiply two elements together that are outside of the prime ideal, so you take a little a and a little b that are in the larger coefficient ring capital R here, and you multiply them together, and they're not in the prime ideal capital P, so they're outside of that, they're in the complement of the prime ideal. If you multiply them together, then you must end up with an element that is outside of the prime ideal. That's the definition of a prime ideal. You cannot multiply two elements that are outside of that prime ideal together and expect to get an element that is inside the prime ideal. Indeed, if you want to multiply two elements together and get something that's inside the prime ideal, then you must use one of the elements that you're producting together must already be an element of the prime ideal. Okay, so that then is the definition of a prime ideal, and again it applies to an arbitrary non-zero commutative ring. Okay, it's just an ideal that, in addition to being an ideal, obeys this additional property that you cannot multiply two elements outside of that ideal together and expect to get something inside that prime ideal. Okay, right, so that's a reminder of what the definition of a prime ideal is. So if you want to show this polynomial p of x is irreducible, what you need to do is search through all of the prime ideals you can possibly come up with for your integral domain, capital R here, the coefficient ring, okay, and try and find one such that all of the coefficients, okay, apart from 1, it doesn't need to be the case that 1 is in that prime ideal, but all the coefficients from p0, p1, all the way up to pn minus 1, they all have to be elements of that prime ideal. But you also want it to be the case that p0 is not an element of p squared. Okay, so the first bit's easy. I hope you can understand what it means for all of these coefficients to be within that prime ideal. What does this second line mean? Okay, what does it mean for p0 not to be an element of p squared? What does p squared mean? Okay, well, p squared is the set that consists of all things of the form x times y, okay, where x and y are both elements of the prime ideal, capital P, okay, so that's a fairly intuitive definition, okay, it's just all of the things that are of the form an element in here multiplied by another element in here, okay, so that's a fairly intuitive thing for p squared to actually represent. Okay, so to construct this then, what you need to do is take every possible element in the prime ideal capital P as your x, and let y vary over every single element in the prime ideal. Take every possible multiplicative combination you can, get all of the answers, collect them all into a set like this, and that's the set that's going to be called P squared. Okay, and of course, because multiplication in an ideal is closed, then you will end up with a subset of P. Okay, so P squared here will be a subset of P, like so. Okay, I won't colour it in green because the entire ring is coloured in green. I'll colour it in orange instead here. Okay, right, so that is the statement then of Eisenstein's criterion, that this polynomial, which is a non-constant monic polynomial in the ring of polynomials over an integral domain, will be irreducible. You can prove that it's irreducible if you can find some prime ideal capital P that contains all of the coefficients p0, p1, all the way up to pn minus 1, but doesn't have p0, the constant coefficient, in the prime ideal squared. Okay, it's square. Okay, if you can find that, you're in business. You can conclude that the polynomial p of x is irreducible. Okay, so before we prove this, let me give you an example of using this so that you utterly understand the actual statement of Eisenstein's criterion. Okay, so we need some ring of polynomials over an integral domain. What's our favourite example of an integral domain? Of course, it's the integers. So let's take some polynomial that's in the ring of integers. The ring of polynomials over the integers. So I need a non-constant monic polynomial, so I have x to the 5 here, and then we'll just make it simple. So we'll have plus 10x plus 5 here, okay, and it is in the ring of polynomials over the integers. So I hope you agree that that is an element of the ring of polynomials over the integers. The coefficients here are certainly all integers. Okay, it is a non-constant polynomial and it is a monic polynomial. So I will be able to conclude that this polynomial is irreducible if I can find you a prime ideal, which is a prime ideal of the coefficient ring, which is the ring of integers in this case, such that my coefficients that are on the lower than the highest degree terms are all in that prime ideal, okay, and the constant term is not in that prime ideal's square. Okay, so let's work this out then. Okay, so my claim, and I've concocted already the prime ideal that this is going to work for. I've selected this polynomial so that it will be irreducible, so that I can find a prime ideal. Of course, usually the difficult bit here would be finding the correct prime ideal. Okay, I already have the prime ideal, so I'm going to tell you what the prime ideal is. So the prime ideal is going to be the principal ideal generated by 5, and you might have been able to spot that for yourself. Okay, this is going to be the subset of the ring of integers, which is all integer multiples of 5, and it is indeed, of course, it's an ideal, but it's also going to be a prime ideal because 5 is a prime number in the integers, and therefore the ideal, the principal ideal that it generates is going to be a non-zero prime ideal. So indeed, the principal ideal generated by 5 is going to be a proper prime ideal of the ring of integers. Excellent. Now what I need to make sure of is that all my coefficients, except the one that's in front of the highest degree term, are in this prime ideal. Okay, of course that's true because 5 and 10 are the only ones I need to check, and they are of course in the prime ideal here. Okay, and of course the coefficients of all the other powers of x are just 0, and of course 0 will be in any ideal because any ideal is a additive subgroup, so it will contain the additive identity, so you don't need to worry about the ones with 0 as their coefficients. Okay, so 5 and 10 are going to be elements then of that prime ideal. Okay, and then, so it's all going well, it's all looking good, my coefficients are in the prime ideal. Now what I need to consider is the constant term here in the prime ideal squared? So we need to consider what is the prime ideal squared. So this principal ideal generated by 5, this is my prime ideal. What is its square? Okay, so just applying the definition here, its square is going to be the set containing all elements of the form an element from the prime ideal times an element from the prime ideal. A general element from the prime ideal looks like 5 times some integer. So I'm taking 5 times some integer and multiplying it by 5 times some other integer, which I'll call z bar. Okay, so I'm just taking a general element in my prime ideal, the principal ideal generated by 5 in this case, and multiplying it by another general element in my prime ideal, the principal ideal generated by 5 in this case. Okay, and I'm taking all of these elements, and z and z bar here are just elements of the integers now. So this is what this set's going to look like. Now, we can apply the fact that multiplication in the ring of integers here is associative and commutative, okay, to rearrange this somewhat. So we'll get that this is the set containing all things of the form 25 times z times z bar, where z and z bar are allowed to vary over any element of the integers. Okay, but you might as well just get rid of this z times z bar and replace it, let's say, with z double bar, okay, where z double bar can just vary over the integers, because the reality is here that z times z bar is always going to be an integer. Okay, and I'll just move this up a little bit so you can actually see it. Z times z double bar here is always going to be an integer. The answer to that is always going to be an integer. You can't multiply one integer by another integer and expect to get something that isn't an integer. Okay, the ring of integers is closed. And you can also make this equal whatever integer you like. Okay, because just set one of them equal to 1 and then the other one equal to whichever integer you like. So in reality, this slot here is just varying over all the integers. So we might as well just simplify it and say this will be the set of all things of the form 25 times an integer, okay, where this integer is any arbitrary integer. That's the exact same set as you would get if you actually had z and z bar varying over the integers here. You wouldn't suddenly end up with a bigger set. You can't, okay, because overall z times z bar just ends up varying over all integers. Okay, so this actually just becomes the principal ideal generated by 25. Now, 5 is not an element of the principal ideal generated by 25. This is all integer multiples of 25 here. Okay, 5 is not an integer multiple of 25. Okay, it's a fifth times 25, but a fifth is not an integer. Okay, so 5 is not an element of p squared, therefore, and therefore this has perfectly met Eisenstein's criterion. I have my non-constant monic polynomial here, and I found you a prime ideal of the coefficient ring here, such that all of the coefficients except the one in front of the highest degree term are in that prime ideal, and the constant term of my polynomial, the constant coefficient, is not actually in the prime ideal squared. Okay, so I can now conclude this polynomial is irreducible in the ring of polynomials over the integers. Okay, so there's an example of actually using Eisenstein's criterion, and I hope that sort of settles in your head exactly what the criterion says. We'll have a break here, and in the next video what we'll do is actually prove that Eisenstein's criterion is true.